like bad sampling properties, such that like any observed data we have tend to be skewed on this scale, and the magnitude of skew and the amount of variability in it tend to be influenced by where you are on the scale. So it's a challenge for doing inference on that scale. So a thought is to convert proportion into odds. The odds, say we've got p equals 0.4. Odds is p over 1 minus p. So if it's 0.4 over 0.6, odds is going to be, anybody? It's 2/3. Yeah, there we go. So equals 2/3. So odds for a low value of 0.4, or sorry, medium value of 0.4 is going to be something like that. If we had let's say 0.9, p equals 0.9, odds equals 0.9 over 1 minus 0.9. So it's something very, yeah, 0.9 over 0.1, which is 9. If we had the inverse, p equals 0.1, odds equals 0.1 over 0.9 equals 1 over 9, something very close to 0. And if we had odds of 0.5, p equals 0.5, that's going to be odds of 1, right? Okay, so for really low odds, we're going to get a really small number. So, but critically, it's never going to be 0 because as this top thing, well, it actually can be precisely 0. If the top thing were 0, the bottom thing would be 1. So 0 over 1 equals 0. Up here, as we get to larger values, say the top thing were precisely 1, it would be 1 divided by 0, which is not defined like in math at all. So in theory, if it were 0.99999 really long, that's going to be a number really close to infinity, but not quite infinity. And then as soon as you put a 1 up there, it just becomes undefined. So the scale is going from really low probabilities yielding zeros to really high probabilities yielding really large numbers. And then the special case of equal probabilities is an odds of 1. So what that means is that our original scale of 1 to 0 gets converted to odds of, again, 0 to infinity. So that's like a little bit better in terms of like the math, but it turns out that it's still not ideal. And because if you notice, like equal movements away from 0.5 being sort of a nice sort of equality point, equal movements away from 0.5 in favor of 1, changing the proportion from 0.5 to 0.9 jumps it up by a whole bunch, so from 1 to 9. But moving from 0.5 to 0.1 moves it down only to 1/9. So you've got, like, if you imagine where the, on this scale, 0.5, 0.9, 0.1. So an equal jump in this range yields, I guess, 0.5, or sorry, I guess this would be 1, This would be 1/9, and this would be, well, it's obviously not super close to infinity, but 9. So yields a very asymmetric jump in the odds sort of range. A way to eliminate that asymmetry is to express this in terms of log odds. So log odds, remember the log of anything, log of 1 is 0. Oops. And a log, it's undefined for 0, but it can go down to negative infinity, and it can go up to positive infinity. And here, this 0.9, or I guess log of 9, let's see, I guess R will do it. 9. Oh. 2-ish, so 2.1. And log of 1/9 is negative 2.1-ish. So it's made that change symmetrical again. So that's nice. Now, if I actually said, so it turns out for various mathematical reasons, talking about log odds is nice. And where people can kind of wrap their heads around odds, it's the fact that we're jumping 3 levels. People have gotten just used to, I guess. You'll see in papers, people will be, when they have usually an epidemiological like data where you have just outcomes that are binarized, you often see reported results in terms of odds ratios, but the actual data analysis, like the models that have been used, will actually be on the scale of log odds, and the analyst has simply exponentiated the terms in that model to, at the end, get out what the odds ratio was. Critically, odds ratio. So if I have a 2 different odds, so let me do, well, because we already have it. So P of group A is 0.9, and P of group B is 0.1. All right, well, we've already figured out what those odds are. So the odds of group A is 9. Odds of group B is 1/9. So odds ratio equals, I guess, what is it? 9. How would we do that odds ratio? It would be 9 times 1/9, or 9 divided by 1/9. 9 divided by, and then 1/9. Let me actually go compute that. 9 divided by 1/9. Big number, 81.
That's a big odds ratio.
Yeah, big difference. What if we did, instead of this odds ratio, what if we converted both of those to their log? So log odds equals 2.1, log odds of A, 2.1, log odds of B, negative 2.1. And what if, instead of doing a ratio, we just said, what is the difference between these two things? What is the difference between their log odds? Well, that's 4. So delta log odds equals 4.2. All right, so delta of log odds is 4.2. Well, if I exponentiate this 4.2, that is exp 4.2 Yeah.
You're doing 10 to the power of
EXP is, let me actually say, log 9 minus log 1 over 9. So remember, that's where I got this 2.1 bit. The rounding caused me to get out a number that wasn't super close to what the odds ratio was, but when I put in the raw numbers, so 2.1, I could just say x 2.197225, and it's symmetric, so we just say times 2, comes out to basically 81. So we get out the same number regardless of whether we compute the odds ratio all by itself or if we compute the difference in log odds scale and then exponentiate that difference. And that's just the log rule that if you have log A minus log B is the same as A divided by B. So an odds ratio is a difference on the log odds scale. So that's why the math usually for all those things have been expressed on the log odds scale, because all the things that we've been talking about have been the effect that a variable makes in like the difference on some scale. RT is 10 milliseconds higher in this condition versus this other condition. It's been a difference. If you just saw the reports talking about log odds, then you think, oh, we have to start talking about like some sort of change on this on the odds scale reflecting the change in this ratio. But no, it actually is because they were dealing with log odds scale and using all the standard tools for effects as differences, and then converted back to something that is about what people are familiar with. There's no reason they had to stop there. They could have also then translated that back to predictions for each condition's probability of having the outcome, and then expressed what the difference in probability was. I guess that's a judgment call in that literature. Sometimes talking about the odds is better than talking about the sort of underlying probabilities, because the people are bad at thinking about probabilities. Usually low probabilities are discounted as 0. So that's another reason people might be expressing things and wanting to stay in the odds realm versus continuing to do the translation. What does this have to do with our modeling? Well, in order to change all of our models that we've been doing so far to be not talking about a continuous outcome, but a binomial outcome, all we have to do is, first of all, get rid of this noise parameter altogether, because we're saying that each outcome is just some binomial event. It's either 1 or 0, so there's no noise at the level of the outcome. So we just remove noise wherever it was. And we're no longer dealing with a normal outcome. We're dealing with a Bernoulli-Logit outcome.
Where else was there noise in the...
It was here normal. We had to use noise in our generative model. It was up here as a prior, and it was up here in the parameters.
Okay. So under the variables to store the parameters, we get rid of almost all of that.
Yeah. In fact...
Oh, no, get rid of all of it. Isn't it all of it?
Sorry? Here, actually, just to be clear, I'm going to undo... Well, no, I don't want to undo that, because So noise was there, and noise is there. I'm going to create a copy.
Yes.
Within long binomial We'll open it. Make it big. So lines 33 to 34, where it just talks about noise, I get rid of that parameter. New line 55, get rid of the noise parameter there. Now we're going to change the whole sampling statement here. So it's going to be a function, some function. That function isn't going to have a noise parameter, so I get rid of that. And the function is this Bernoulli logit. The logit part means that the thing on the inside is expressing a log odds. It's expressing something on the scale of log odds. And the Bernoulli part is saying that the thing on the inside is a log odds. Flip a coin with, and the outcome is a coin flip with this log odds of success. So if the thing on the inside were, for this condition, they had a log odds of 2, it would be around 0.9-ish. It would be flipping a coin with a 0.9-ish probability of success, but it still is getting either a 1 or a 0 as an outcome. Success being a 1, 0
gotcha.
being not success. So this Bernoulli part is just expressing we're doing a coin flip. The thing on the left-hand side of the squiggle here is therefore expected to be 1s and 0s. Similarly, we actually wouldn't want to do any of the scaling that we did, so you can delete all of the generative quantities. And ditto, you'd want to delete all of the transform data. ZY was down here. You could just say Y is the outcome. And one picky thing that I don't think was necessary when they made this language, but whenever you use this Bernoulli logit, it wants to be really sure that the thing on the left-hand side is 1s and 0s, not anything else. So up here, when we say that Y is a vector, we actually can't use this syntax. I'm going to copy it and put it down here, and I'm going to comment it out. So this was the old way of doing things.
What keys do you press to comment it all out?
Oh, Command-Shift-C. In a Stan document, that's going to put not a hash, but 2 slashes. But Stan recognizes both of those as comments. So this was the old thing for something that's continuous. The new thing, int y, and the square brackets on the right side of the y. This is like saying y is a vector of length ny, but all the contents are only the integers. Now, it's also happens to be the integers 1 or 0, so you could.
When we
Go ahead.
prepare data for Stan, we have to feed it data that is 1 and 0, 1 and 0s. Like we
Yeah.
can't use the data we already used this class because it wasn't 1s and 0s.
The RT, you wouldn't be able to use the RT column, but you could use the error column because that is the 1 and 0.
And it doesn't just require it to be like it has to be 1s and 0s, right? It can't be coded like 1, 2, 1, 2, like.
Yeah,
Yeah.
you need to
Yeah.
convert it to 1 and 0. Yeah.
Okay.
Now, a trick is that if you have trues and falses,
Mhm.
you just say as numeric, my column full of trues and falses, and that turns all the falses to 0 and all the trues to 1. So that's a trick.
Any chance it also does that with yeses and nos?
No, you'll have to do an if-else
Okay.
for that.
That a joke.
But yeah, that does that model. So I'm going to save.
When I click check on save, it's like,
Ooh, ooh.
I'm wondering if the one
Well-
was much shorter, and I'm wondering what I'm missing now.
Sorry. Well, so we got rid of the whole generated data. We got rid of the Z noise, the prior on Z noise, and we changed this to Bernoulli logit. We got rid of the generated quantities as well.
For the priors on population parameters, we can get rid of the Z, right? Because we don't transform in this.
Yes. Yeah. Good call.
Not that it doesn't really make a difference.
Yeah. You can actually just do a find and replace for Z and replace all with nothing. That should do just fine.
Can you scroll to the bottom? I'm getting
Okay. What does your error say?
first it says no matches for vector Bernoulli.
Oh, okay. So did you do this bit above? Saying y is and you come check. Can you do the same? Do a find and replace on Z. I'll save.
Getting an error still.
Okay.
I did the find and replace all sets. Oh, whoops. Oh, I was looking for that one. Yeah. Oh, okay, perfect. And so that's if you have a dichotomous outcome variable. What if you have a dichotomous independent variable?
Let's see. Well, isn't that what we had when we narrowed down Q to just 2 levels?